And hello YouTube, welcome back to our radiation heat transfer learning journal. So in this video we're going to continue where we left off. I've taken quite a hiatus from the last time because I was doing other stuff, but now I'm back and doing radiation heat transfer. So let's continue where we left off and do some recap. And as you noticed, I'm not using Microsoft Word anymore to do my presentations, but rather I'm going to be using a mixture of software in Linux, such as Lix and LaTeX. So yeah, that's what we're gonna do today's video. What today's video is about. I'm gonna continue from where we left off and hopefully move into some of the more practical aspects of radiation heat transfer, because as we saw in the last few videos, analytical solutions are quite tedious and quite limited in scope, meaning to say you cannot do anything more than simple geometries and simple cases. Now the moment, like for example, you throw in scattering, the equation gets much more complicated to solve and you have to do some iteration. So yeah, that's what we have. That's the problem we have. So yeah, I've converted my whole Word file into LaTeX, so it should be looking a little bit nicer. Nonetheless, there will be formatting errors nonetheless, but hopefully it should display mostly right. Okay. So just to recap what we are doing, so this is the radiation transport equation, radiation heat transfer equation. So it's basically if you are looking at a beam of radiation going in one direction, of course you can discretize by spectrum as well, but we'll take out the spectral part, so not so much of an issue now, but this is what the equation looks like. So this is how the radiation the radiative intensity actually changes as a function of the optical thickness. So as it passes through a medium, there are a few things that can happen to it. Firstly, we will have, if the medium is hot, then it will add to that radiation. That's what this term here is for. If there is scattering in from other angles, so for example, let's say okay, let's take out the drawing tool. So instead of paint, we have drawing now. This is Linux. So let's say you have some radiation going this way, and this is your direction of consideration. So at some point there will be some scattering. So the scattering can go from this original direction over here into this direction, so that is known as in-scattering. So you don't just consider in-scattering from this angle, you have to consider in-scattering from many angles. Okay, and that's how you arrive at what you do. So yeah, so where were we? Yes, basically we sum all the in-scattering from everything, and this is known as we sum all the in-scattering from various directions, and we call this an in-scattering term. And this is the extinction term, which is a combination of absorption and scattering out of our prime direction, the direction we are considering. And just for you to remember, this is what our albedo actually looks like. Albedo is actually the ratio of the scattering term, the scattering coefficient, to the extinction coefficient, where the extinction coefficient is actually the scattering coefficient and absorption coefficient added together. So this is the albedo, which is how much of the beam attenuation is due to scattering as compared to absorption, or absorption and scattering. It's the whole thing. So if we see this tau lambda, and just refresh, it is actually our beta lambda, and you integrate it from 0 to whatever distance you are talking about. So we already said that RTA is very hard to solve for 1D cases. How can we generalize it for more complex geometry? Alright, so that's the big question. And of course, we want to understand why it is hard. And the main thing why this radiation transport equation is hard is because of this term over here. Okay, this in-scattering term makes solving the radiation transport equation very hard because of this big integral here. And that makes normal solving a little bit hard. So we have to do some sort of numerical integration of some sort to actually deal with this term. Okay, you have to deal with this term. Of course, the other reason why it is hard is because, you won't know what your temperatures are of the medium, and that will affect your black body radiation thing, your black body radiation. As you travel through the medium, different parts of the medium, like if you travel from, okay, let's clear everything. Yes, okay, that's good. Let's say you have radiation traveling through some medium. The medium here may be at different temperatures, right? So T1, T2, and T3. So at this point, for example, it will have some black body radiation, which is based on T1. This one will have a black body radiation that is characteristic of T2. This one will have some black body radiation characteristic of T3. Now the thing is that you have to know what T1, T2, and T3 is, or else, you've got to do some iteration, and that's where the numerical solutions actually come in. So long and short of it, just like the Navier-Stokes equation, that's a fluid mechanics one. This radiation heat transfer, you also have to use some numerical methods. But even with doing those numerical methods, you still have to deal with this integral term. And how do we do this? So to deal, okay, delta should be deal. So let's find where delta is. Okay, so I need to deal with this term. So I will make corrections later. To deal with this term, we need some approximation methods to help us approximate this integral. And in summary, two of the most popular classes of methods, they are called the discrete ordinates method. Sometimes it's called SN. SN is the name of the method. Okay, and we have spherical harmonics method, which is called PN methods. So I'll try to go through the spherical harmonics because that's a very popular method. And we'll see how we can go from there. And discrete ordinates is actually used in OpenFOAM, if you use OpenFOAM. And if we got time, we'll go through that method as well. However, these methods are computationally intensive. So there are more simplifications where we can assume the radiation medium is optically thin or thick. And those are some other simplifications we use. So the idea behind optically thin medium is that we kind of ignore the case of the extinction. We say that this extinction term is negligible in optically thin medium. So what happens is that the radiation intensity it will increase due to black body radiation and in-scattering, but this extinction term we just neglected because it's thin. So that's for very small tau. For optically thick medium, the main idea is that all of a sudden we realize our medium is so thick that you can treat this as a diffusion equation. So in optically thick medium, we call this the diffusion approximation. Where you can treat this additional radiation heat transfer as if it were a conduction problem. So these are the two extreme cases we have, but I prefer to go into some of the more complex methods before we talk about optically thin or thick approximation, because these are the methods you'll find in solving software. So I want to dive into them first. This one is just for foundation building, but in terms of knowing your theory well, and that's just making sure you know your theoretical foundation well. But most cases you solve are not going to be so simple. So I'll just jump straight into where the meat is. So first thing we want to build is some foundation for our spherical harmonics and discrete ordinates method. Then this is known as the moment method. It's taken from Michael F. Modest, one of his chapters there, and you can take a look at some of these links here. It will tell you what the method is like, but I'm not going to go through those PowerPoint slides. Okay, so this is also known as the Mount-Eddington approximation. This is, I think, a subset of the moment method. Okay, and it is important to know the moment method as sort of a baseline to understand spherical harmonics. Okay, so it's to tell you, what are you doing with this equation. All right, so what's the it's to give you some foundation to start spherical harmonics with, because spherical harmonics itself, it may be a bit intimidating to start. So let's start with something simple first. Okay, something a little bit more simple, then we jump into spherical harmonics. Alright, so what is this about? So picture you have your radiation transport equation, and for simplicity's sake, we are not going to care too much about wavelength here, but you can take it on a wavelength basis. That means you look at this radiation transport equation and talk about one simple wavelength, or you can just ignore wavelength altogether. So we take a gray medium approximation for simplicity's sake. Okay, so either gray medium or spectral basis. So let's say I evaluate one part of the spectrum, or just consider it gray. Alright, so we have this equation here, our usual absorption, extinction, black body term and inscattering term here. No source term, no nothing, just those. Now what can we do about this? Now the difficulty is still that this angular dependence, because of this what do you call that? Because of this radiation inscattering term. That will often cause a bit of annoying effects. So here's the idea. Let's try to integrate this intensity over all angles and try to get a transport equation out of that. So our new quantity, so instead of calculating an equation in terms of this intensity, because this intensity has it has direction involved, we can integrate out this direction and just ignore the direction completely, so to speak. Of course, we will lose some information there, so we will need to make up for it. So here's the idea. We integrate the flux, or I'd rather say intensity here. Okay, so I'll look for, let's integrate. Okay, so I'll say intensity. Say intensity over all angles. So the final LaTeX file should not display that. Anyway, so we have this here. Okay, so let's integrate. Integrate with respect to d mu. So let's integrate with d mu throughout this equation. So let's do a simple case first. We will take a 1D plane parallel case. In that case, the above equation, this equation actually reduces to something like this. On the left hand side, we actually see the mu over here pop out, because actually what happens is that basically we have ignored the azimuthal part of this. We integrate out the we take out the azimuthal part, so to speak. We say that there's azimuthal symmetry, and of course and we actually make this whole equation in terms of tau lambda. tau lambda is right. Let me draw out here. So you have two things here. So let's say you have a beam of radiation going like so, and you have a tau s lambda being like so. Okay, let's okay. So anyway, sorry about that. Okay, so that is tau s. So if we have the direction here of theta, okay, theta from the normal, we like to actually consider this distance for we actually like to consider this optical thickness over here. So as you can see, tau s equals to tau over cosine theta, right? Tau over cosine theta, and we like to say mu equals to cosine theta, and that's why we kind of let it pop out. So when we change the variables like so, from tau s lambda or tau s to some tau, so tau is actually this so-called vertical distance, we actually bring this little mu out here. Everything else actually remains more or less the same. So for the scattering term, we integrated out the azimuthal part, and for this part we actually changed the variables from tau s lambda to tau lambda, or tau s to tau. So tau is actually this vertical distance we see here. Okay, so that's part one. And after that, after integrating, just remember this is why we were changing the coordinates. Okay, so now we want to integrate the whole thing throughout with mu, just like what we were saying earlier. So we don't want a transport equation that deals with the intensity anymore. We want a transport equation that deals with the integrated form of this intensity. So we integrate throughout by d mu from mu equals -1 to mu equals to 1. That will cover the entire polar angle. That means cos theta equals -1, which is, I believe, minus 90 degrees, okay, or minus pi by 2, all the way to pi by 2, where cosine theta should, oh no, it's not pi by 2, sorry. It should be from 180 degrees, which is pi to 0. So it is 0 to pi, but you kind of switch things around here. So it's mu from -1 to 1. Mu equals -1 corresponds to we have this -1 to 1. Okay, -1 corresponds to 2, corresponds to pi. 1 corresponds to 0. Okay, mu equals 1 corresponds to the angle being 0 in radians. So we do this integration throughout. It's not too big an issue. So and to make things nicer, we just multiply things throughout by 2 pi. Why is this so? We will see later. Okay, so actually there's no need to talk about it later. We can introduce this term now. So we can introduce this so-called integral term, all right, as I0. Okay, I0. I0 is actually this quantity we are talking about. We integrated out the directions, and then we just put a simple 2 pi in front. Okay, so you just put a simple 2 pi in front, and yeah, basically we just do the integration very simply. So what can we do? All right, we notice that this term on the right hand side here actually just reduces to this I0 quickly. So that's why the rightmost term, which is the extinction term, it just becomes minus I0. So that's one term already dealt with. So next term. Okay, next term is this term. This term is, it should also be kind of you know, it is like another term. It is what we like to call we need to deal with this annoying term right over here. Okay, this should not be I0. All right, I should kind of delete that line out. So this is a typo here. Never mind. In the last we can deal with that later, the typo, because I'll need to generate a new PDF file. Okay, so I'll edit it in LaTeX later. But we have this annoying term over here, this 2 pi blah blah blah, this term over here. So we need to introduce a new term to help us to deal with it. So we'll call this I1. So I1 is actually very similar to I0. I0 is this integral term here, except now that we have the mu inside. Okay, we just call this I1. So this is whatever power mu on the inside is, that will be the index over here. Okay, so for example, I2 will be 2 pi, then the integral of mu squared times I lambda tau lambda d mu. Okay, so likewise I0, okay, the power of mu here is to 0. That's why you just have 1, and you will just reduce to this expression here. So these terms I0 and I1 are called the zeroth and first moments respectively. This is why we call this method the moment method. Okay, so that's it for now. I'll stop for the time being. I'll get back to continue this presentation a little while later. Thanks for watching. I'll see you guys again. Bye bye.